We're going to talk about areas in a bit more detail because there is a difference between an integral and an area. Now we use integrals to find area, but there is, as I say, a difference. First of all, let's talk about areas below the x-axis. As we mentioned yesterday was, well, if it's above the x-axis, we know the integral will give us a positive number. If it is below the x-axis, the integral will give us a negative number. So alright, going from A to B, for instance, is completely above the x-axis. So I know that will be a positive amount. Everything's good. I can just use the integral and get the answer. But if I was going from B to C, we need to make sure, are we talking about the integral or are we talking about the area? Because we're below the x-axis. So we know that integral will give us a negative number. So that will not give us the area. To find the area, we will need the negative of that integral to bring it back to being a positive number. Now, if it is below the axis, the area will be the negative of the integral. Area below the x-axis, I say, could be the negative. Other ways you could do it, you could go, oh, well, it'll be the absolute value of the integral. Well, then you're always going to get a positive number. That'll certainly be true. And of course, the other way we could do it is swap the limits round. Because we saw that if we swap the limits round, then we change the sign of the integral. So if I want to turn it into a positive number for area, swap the limits round. Well, let's do the x cubed one. The area, which is different to the integral. Now, if it was just the integral from -1 to 1, we know the answer would be 0. Because we've got this odd function, those areas are equivalent. They would cancel each other out. But if it's an area question, well, the answer is not 0. Clearly, if I said, what's the value of that area that we shaded in, the answer can't be 0. There it is, it exists. It has some value. The bit below the axis has to be negative. So I write two integrals, one for where it's below, one for where it's above. So from -1 to 0, it's negative, and from 0 to 1, it'll be positive. I integrate, and obviously the actual primitive function's the same for both, and then substitute into each of those. We come up with our answer of a half. Of course, I could still use the idea of symmetry, because I do know that these two areas are the same. So I could treat it like I would with an even function, so actually it's going to be twice the value from 0 to 1. And again, we integrate and we come up with the same answer. Well, that works if the areas are the same, of course. Let's have a look at this one. So we've got a cubic, there it is factorised, x plus 1, x plus 2. So from -2 to 1, we're above, so it'll be plus that integral. From -1 to 0, we're below, so it's minus that integral. This time you'll notice I decided to swap the limits around on the -1 and make it a positive. Now the advantage of doing that, it's a very small advantage, but it is an advantage, because you'll now notice the top limit on both of these are the same. It saves me one substitution, because I can say, well, look, I'm going to get twice what I get when I substitute in -1, because I'm substituting -1 into the first one and into the second one, and it's the same primitive function that we're substituting into. So I can say it's twice those, but then minus what we get when we substitute in -2, and minus what we get when we substitute in 0. Okay. Very small time saving feature, but you know, we could take advantage of that. Well, what about if we could go into the y-axis rather than the x-axis? So this is the particular area I'm interested in. We do everything with respect to the axis that we're going to. So in this case we're going to be doing everything with respect to y. Now what that means is the equation of my curve, which at the moment is y is the subject, we need to make x the subject, because then it will be in terms of y, it'll be with respect to y. So the first thing we need to do is to rearrange our function and make it x equals some function of y. Then it's the y coordinates we will substitute in to find the area, because again everything's with respect to y, and our formula would become this. So the area now is we're going from c to d, the y values of function y with respect to y. The way I tend to remember it is, well, if I'm going to the y-axis, then it's dy. If I'm going to the x-axis, it's dx. Let's do an example of that then. Here's our quartic, y equals x to the power of 4, but this is the area I'm interested in. Now I know the x values, but I'm going to have to rearrange, so x will be y to the power of a quarter. I will need to know what those y values are, and they turn out to be 1. When we substitute in 1, we get 1, and 16. When we substitute in 2, we get 16. But other than that, now it becomes exactly the same. We're just doing it with respect to y instead of with respect to x. Add 1 to the power over the power, substitute in, and we do get a nice answer of 124 and 5. And you might notice I didn't bother putting it into surd form this time. The main reason I didn't is because I know that I can find the 4th root of 16. It's an exact value, so I didn't worry about putting it into surds. I knew the calculator would handle that. What if we're not going to either axis? We're just going between two curves. So two curves end up trapping some area. So here's y equals function x, and I've got a second curve, g of x, and I want to know what area is trapped in between the two. Now I could go to either axis. I could do it with respect to x, I could do it with respect to y. It really doesn't matter. I should come up with the same one, but I want to pick the one that's going to be easier. I'm going to go to the x-axis because that is going to be easier. Now how do I know? You look at the two curves and see if the boundaries change. What do I mean by that? If I'm going from A to B, all the way from A to B, the red one is on top of the blue one. But if I was to go with respect to the y-axis, so imagine travelling that one. Now it's just blue, 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 but hang on, it changes. Now it's red to blue. So it changes. I'm going to have to put more thought into that question. Let's do the one that's easier. Let's do the one where it doesn't change. So I'm going to go red to blue. Basically, I just find the area under each of those curves and then subtract. And that'll get me the difference between the two. So I'll find the area under the first curve, so the red one, minus the area under the blue one. That'll give me the area I'm looking for. The limits are the same, of course. A to B, function x minus g of x. But we can recombine that into one integral, and that's what we have to find. Function x minus g of x. Now if you don't have a picture, how do you know which one's on top? Well, you probably won't. But if you end up with a negative number, then you've probably put the wrong one on top. Let's do this one. Area enclosed between y equals x to the power of 5 and y equals x in the positive quadrant. So the first quadrant is what they're talking about, when both x and y are positive. I always like to draw pictures so I can visualize what I'm doing. Y equals x is of course our straight line. X to the power of 5 is that cubic type shape. I mean, it's not a cubic, but has that same sort of inflecting shape to it. We just want the area in the positive quadrant, the first quadrant, so it's just in that section there. So I've got the blue line minus the red curve. I'll need to know the point of intersection because I'm going to have to substitute in that value. When does x to the power of 5 equal x? Well, if we're unsure, we can go and solve it. But 3 points. Obviously, the one over here is -1, then 0, and then +1. So we're interested in +1. Top one minus the bottom one. X minus x to the power of 5. We're going from 0 to 1. Let's just integrate. Add 1 to the power over the power. Substitute in. We get our answer, 1/3. Let's look at some HSC ones. This came from 2002, quite a while ago now. We have a parabola and a line, and they were very helpful to us. They told us all the information. Y equals x minus 4, the parabola is x squared minus 4x, and they even told us the points of intersection. At the point 4, 0, oh, it's missing a word there, it should say and A. Well, A is the other point. Find the coordinates of A for 2 marks. I said they were very generous. Find the coordinates of A for 2 marks. Okay. Well, in order to do that, I would solve them simultaneously. When does x minus 4 equal x squared minus 4x? A little quadratic to solve. But I already know one of the answers. I already know one answer is going to be 4. That helps me in the factorising. X minus 4, x minus 1. So the other one must be when x equals 1. And they've asked for the coordinates, so I need the y value as well. So it's the point 1, -3. Find the area of the shaded region. So the bit in between the two. Okay, well, the line is on top, the parabola is on the bottom. X minus 4 minus the parabola, we're going from 1 to 4. There's our quadratic that we are going to integrate. Primitive function, substituting in 9 on 2. Now here's an interesting thing. You'll notice the picture. It's all below the x-axis, but I ended up with a positive number. You see, when you're going between the curves, it doesn't matter whether it's above or below. You're still going to get the same answer. Because what I could have done, at this stage we had a parabola and a line, and that's the area I had to find, and everything was below. And I won't write the whole equation down. Let's just call this y equals function x and call this y equals g of x. And we said we're going to find the integral of function x minus g of x. That's what we said we were going to do. What I could do is shift the whole curve up as much as I like. I'm going to shift it so it's all positive. Now, I'll shift it up however far. Nothing's happened to that area. It's still the same area. And those points of intersection are still the same x value. I'm doing it with respect to x. I don't care about the y value. But what would the equation be? Well, this parabola is now y equals function x. Let's say we shifted it up. Oh, let's go crazy. Let's say we shifted it up 100. And this line would be g of x plus 100. And then I'd say, well, I want to find the area. So it'll be the integral of function x plus 100 minus g of x plus 100. Oh, 100 minus 100 disappears. Function x minus g of x, we get exactly the same answer. So when it's between two curves, doesn't matter. We don't have to worry about, is it going to be negative, is it going to be positive? We just go top boundary minus the bottom boundary. Alright, let's keep going. 2005 question. Shaded region, we've got a circle and a parabola, and there's the interesting area they want us to find. Find the area of the shaded region. They gave you a hint by considering the difference of two areas. Well, yeah, that makes sense, because if you look at it, the boundaries change if I do it with respect to x. So I would have to break it up into two different areas to work out. Let's say there, I've got the circle minus the parabola, whereas in the second one I've got the circle minus, well, technically the x-axis. We just go to the x-axis. If I'd gone to the y-axis, then alright, I could have done it that way and gone, it's always the circle minus the parabola. Mind you, they said by considering two areas. I would have only been considering one area if I did it that way. But I tell you what, there's an even better way. Remember, why are we using integration to find area? We're using it because we don't have nice, neat formulas, so we can find those unusual ones. But hang on a sec, I do have a formula for the area of a circle. So I could, for that quadrant of a circle, find that area and simply subtract the area under the parabola from 0 to 1. Now I've satisfied their question. It said by considering the difference of two areas. Yes, I will do that. Might not be what they were expecting. Maybe it was what they were expecting. But I've satisfied what they said. So now it's just, well, a quarter of pi r squared minus this one integral going from 0 to 1 underneath the parabola. Well, a quarter of pi r squared turns out to just be pi. And add 1 to the power of the power, substitute in, and there we have it, pi minus 5 on 6 units squared. 5 F and G, playing with areas, all different types of areas.